Okay, this one is about hybridization. Where is it? And maybe some polarity. All right, so hybridization is a theory about how these bonds actually are formed. Okay, so if we're looking at something like HF, H has one s electron, and F in its valence shell looks like this. Okay, so basically F is full except for this 2p orbital, and H has a 1s orbital. So how do these bonds physically form? We've got a hydrogen with an 1s, and we've got a fluorine with a 2p, because remember, p's are shaped like a dumbbell, and then that overlap is what we assume is the bond. Well, that's great, until we start dealing with things that are a little bit more complicated, such as CH4. Okay, here are some problems with this. Okay, carbon's valence shell is 2s2, 2p, 2. Okay, so its s orbital is already full, and its p orbital has 2 electrons in it, and then one that's empty. So carbon makes 4 bonds, and it looks like it can make like 3 based on this, because it needs to fill something here, but then it has this empty. So let's say that maybe it takes one of these and promotes it and brings it up here, and then it would be able to make 4 bonds. Okay, but one of them would be from the s overlapping the hydrogen s orbital, and 3 of them would be from p orbitals. Remember, there's one on the x, one on the y, and I'm sorry for my terrible drawing, one on the z. Since they're on the x, y, and z axis, they are 90 degrees apart. That's actually not too bad. You can kind of see that in 3D. They are 90 degrees apart. Well, what do we know about this? Well, Vesper says that these are 109.5 degrees apart. And we know that each of these bonds, this one, this one, this one, and this one, are all exactly the same. They're all equivalent. And it would suggest that if I had an S overlap versus a P overlap, that would not be equivalent. So there's something wrong here. There's something that this model of these orbitals overlapping, there's don't completely work. So the scientists came up with they adjusted their model. Okay, so here's what they picture. They picture that the atomic orbitals, which are S and P, okay, they get hybridized. And when we think of hybrid, we think of a combination, okay? So I want you to picture, like, this is terrible drawing, but an orbital blender, okay? So I take some s orbitals and p orbitals and I put them in the blender, and then they come out all mixed together. So here's the theory. The theory is that for CH4, for example, okay, CH4 has 4 domains, right? It's tetrahedral electron domain geometry. I'm sorry that I spelled that wrong, but that's okay. So what we think it does is we think it takes 1 s orbital and 3 p orbitals, and it puts them in that atomic blender. And we have 4 atomic orbitals total. I'm going to get 4 hybrid orbitals out, 4 sp3, right? 1 s and 3 p. Something like CH2O, okay? I have 3 domains around it. So what is it going to do? This is something that's trigonal planar, okay? It's going to take 1s and 2p orbitals. And it's going to mix them together in their blender. I have 3 orbitals in, I got to get 3 orbitals out. I get 3 sp2 orbitals. Okay, something like CO2, I have 1 s and 1 p orbital that go in, and I have 2 sp orbitals that come out. And I think I showed you this earlier. These are actually on your magical sheet of all that VSEPR stuff and the shapes and the bond angles. You need to know how something is hybridized. Okay, what this theory does is it explains how all of these bonds are equivalent, because we mix the orbitals together, and each one of these is an sp3 orbital. And then if I have 4 orbitals around that central atom has 4 orbitals, they're going to arrange themselves as far away as possible, which is 109.5. Same thing with 3 orbitals as far away as possible, that'd be 120. And this is where your bond angles come in. And 2 orbitals, that's going to be 180. Here's what you need to know about hybridization. 1, you need to know that hybridization is the explanation for how all the bonds are equivalent. And you need to be able to tell me up to 4 domains what's the hybridization. Okay? If you are already identifying shapes and you are identifying bond angles, you're going to have to do a little bit of memorization. I'd probably add the hybridization to that memorization. If it's tetrahedral, you need to know that it's sp3. If it's trigonal planar, you need to know it's sp2. And if it's linear, you need to know that it's sp. This is electron domain geometry, not the geometry of the molecule itself, all of the electrons. And you do not need to know anything about hybridization for things that are larger, that have 5 or more. So like trigonal bipyramidal or octahedral, you do not need to know what those are hybridized. Okay? The next thing I wanted to talk about is polarity. Okay, so polarity. We talked about the polarity of a bond. A bond is polar if there is an uneven sharing of electrons. So we talked about the bond between carbon and fluorine, perhaps. Fluorine has a higher electronegativity than carbon, so fluorine pulls stronger to carbon and becomes a little bit negative, and therefore carbon becomes a little bit positive, and this bond is polar, and it's based on electronegativity difference, okay? But the CF doesn't form an actual molecule. The molecule is going to be CF4. So I'm going to have another C bonded to F over here. And that bond is also polar, okay? And this is going to be a little negative, and this guy's still going to be a little bit positive. Then I've got another bond up here. Remember, these are 109.5 degrees apart, but for all intents and purposes, it's the same. So this guy's a little bit negative, and this guy's a little bit negative. Now, if you've taken physics, hopefully you can see, think about this as a free body diagram, okay? This carbon is being pulled this way, and up, and down. And it's being pulled equally in all directions. It is a symmetrical molecule, so if you haven't taken physics, you can think about it as symmetrical. And when I say symmetrical, I mean that it is bonded to the same thing on all 4 sides. So that carbon is bonded to fluorine, 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 fluorine. Okay, so if it is symmetrical, or if you were a physics kid, and you have no net force, right, in your free body diagram, there's no net force, you are nonpolar. If you are asymmetrical, you are polar. So a great example of that is water. Okay? Remember, we are 3D here, so water is bent. It is helpful to draw water bent because it's sometimes easy to mix that up. Okay, now let's look at this. Oxygen is more electronegative than hydrogen, so oxygen gets the electrons more. Oxygen is more electronegative than hydrogen, then oxygen gets the electrons more. Okay, so if we look at this, we have a net force, right? We have a net force kind of like that direction. So this would suggest that this is a polar molecule. And additionally, we can use our symmetrical trick, right? Yes, it's symmetrical this way, but when I say symmetrical, I mean that it's bonded to the same thing on all four sides. So oxygen is bonded to hydrogen, bonded to hydrogen, bonded to nothing, bonded to nothing. So since it's not bonded to the same thing on all four sides, water is asymmetrical polar. A counter to that is carbon dioxide. Here's CO2. Okay, so here we go. We've got oxygen is stronger, so oxygen gets the electrons more. Oxygen is stronger, oxygen gets the electrons more. We can see that this is sp hybridized because it's linear. It has a bond angle of 180 degrees. And we can, it looks like it has no net force, so that would suggest that it's symmetrical nonpolar. Additionally, this carbon is bonded to oxygen, bonded to oxygen, bonded to oxygen, bonded to oxygen. Since it's bonded to the same thing on all four sides, there's no bonds that go to these lone pairs. That makes that symmetrical nonpolar. Okay, that's how you can look at these things. Very typically, if you have a lone pair that is not symmetrical on the other side, if you have a lone pair in tetrahedral, it's pretty polar. Square planar is nonpolar. Let's see what else. Square pyramid is polar. Linear in like trigonal bipyramidal or trigonal planar and trigonal bipyramidal is nonpolar. But take a look at your shapes, and you can usually tell based on the shape of it whether it's polar or nonpolar. But we're really just looking for those dipole moments. That's what it's sometimes called. It's called a dipole moment if it's polar. We'll say it has a non-zero dipole moment, and that would indicate that it's polar. Usually you can see based on the shape alone if it has a non-zero dipole moment, if it is actually polar. Hopefully that helps.